Okay, hey folks, we are getting into this module 7 on mini electron atoms and atomic spectroscopy. I love this stuff as an instructor of general chemistry. I find it to be really cool to come back full circle and get into that stuff that we learned in our very first semester of our chemical education. So you can see I've got a periodic table in here in front of me. We are going to dissect this thing. So learning goal number 1 here of this module, be familiar with the helium atom total energy operator. Let's do it. So here we have modified one of my favorite little cartoons that I generate in this class. We now have helium. And notice our nucleus has been replaced with just N plus to indicate that there are protons and neutrons in this body. And now we have these 2 electrons. So in the orbital approximation, which is what we will subscribe to in this development of quantum mechanics of atoms, a reasonable first approximation is to treat each electron as occupying its own orbital. So we can imagine some total wave function indicated by the capital psi, where now each one of these r's corresponds to the radius of the individual electron, and technically speaking, those are vector quantities with all the appropriate angular information. So by treating these as separable, we can just do that, the separation of variables, where now we'll have a wave function describing each electron nucleus system. So now putting our Hamiltonian together, you can see here that these 2 terms right here, that I will call Hamiltonian number 1. So right, that corresponds to the kinetic energy of our electron, right, that term, as well as the potential energy, right, via Coulomb's law. And now we can see here that we've got another Hamiltonian describing the second electron. And then finally, what you'll notice is we've got this other term right here. And it is a Coulomb's law term. And notice here that it says R12. So now that's describing the distance as a vector quantity between the 2 electrons. So, and you'll also notice that it's got a positive sign, whereas these 2 potential terms have a negative sign. So this positive sign indicates that there is some repulsion going on. So this is the electron-electron interaction, whereas the negative signs in here indicated that there was attraction. So as it turns out, whoa, my handwriting is rough right now. Too much of a break. Okay, let's write that again. Attraction. Maybe just slightly better. So as it turns out, if we ignore this electron-electron term, this wave function can be solved. So let's go ahead and do that. And just to demonstrate that we can use the separation of variables. So if I put all of this together and we say some Hamiltonian operates on our big psi, R1, R2. So now we just kind of put together that Hamiltonian is a sum of the individual Hamiltonians. And now we'll say that my wave function can be separated by its 2 electrons. Okay. So now if we distribute this through, we're going to end up with the following. I've got H1 distributed through to psi R1 times psi R2, and then H2 distributes in the same way to psi R1 and psi R2. So now what we should recognize here, H1 is only going to operate on psi 1. So I can bring terms out in front, right? My psi R2 is not going to be dependent on H1. So I can bring that out in front. So let's do that. Psi R2. And now we have the Hamiltonian 1 operating on psi R1. And then now we can do the same thing over here where we recognize H2 will only operate on psi 2. So I'm going to bring that out in front, psi R1, and then multiplied by H2 operating on psi R2. Well, if we remember our Schrodinger equation, right, let's write the most simplified version, H psi equals E psi. We can see now when H1 operates on R1, that's going to give me back E1 times psi R1. And then when H2 operates on psi R2, that's going to give me E2 and the original wave function, right? So now I'm putting this all together. We can write psi R2 E1 psi R1 plus, that's going to be psi R1 and then times E2 times psi R2. Well, now hopefully we might recognize that because these E's are now eigenvalues, they're just constants, I can bring those out in front. And doing a little algebra, I end up with the following: E1 plus E2 multiplied by psi R1 psi R2. And thus, if we remember in our separation of variables, wave functions are products and energy solutions are sums, right? E1 plus E2 equals the total energy. Then we know this whole thing now just becomes E times big psi R1 R2. So if we could ignore this term, this electron-electron interaction term, we would have a solvable two-electron wave function. And in place of psi R1, psi R2, we can just put in the nominal H1s wave function. Let me make that a little bit better. That is a ket, right? So we could replace psi R1 with the H1s wave function, and we could replace psi R2 with another H1s wave function. And we would see that those wave functions are then just a sum of the two individual radii. But we have ignored this really important term, this electron-electron interaction term. And because of that, using the orbital approximation is just an approximation. And we can only do this on the hydrogen-like orbitals. So in other words, systems that have one valence electron typically work really well in this orbital approximation system. After that, we have to make approximations, which is where the entire field of computational chemistry is born. Okay, folks, I'll see you in the next video.